So let's work an example where we now have a weak acid as the unknown down in the beaker here, and we're going to use 40 mils of 0.1 molar acetic acid as our example, and then the titrant here is again the strong base. So we're titrating weak acid with a strong base. Let's walk through steps and try to understand what the pH at the various regions of the system are. So in this example, I want to start with the equivalence volume. I mentioned this in the previous strong acid, strong base video as a potential starting point. You don't have to do this, but I like to do it just because it gives me a sort of calibration for where I am on the x-axis, because the equivalence volume is really the halfway point of the titration. So if I know what this is, then I understand intrinsically where the pre and the post equivalence regions are. I won't go as far to compute the actual pH yet, but I will just figure out the equivalence volume. And that follows exactly the same process that we used in the previous video, because remember, anytime you're adding acid to base, the equilibrium constant Kn for that neutralization reaction is really large, which means that it's going to go to completion. And that's also true for a strong acid plus a strong base plus a weak acid, like this example. So in this case, we know that stoichiometrically, we're going to have OH reacting with HA 1-to-1, and so this becomes simply an M1V1 problem just like before. So that becomes 40 milliliters of 0.1 molar acid, so this is the HA, or the acetic acid, and then we have X as our volume of titrant, that's our equivalence volume, and 0.1 molar. And just like before, you notice that this is the same concentration, but both in a 1-to-1 reaction. So solving this, X is going to be 40 mils. So we know that is our equivalence volume. We're going to store that away, and I'm just going to put it up here because that'll be useful in understanding where we are in that titration curve. So next logical step is then to figure out, well, what is the pH of just the sample solution before we've added anything? So this is the 0 milliliter condition. Well, we need to understand what this thing is. This is acetic acid, which is a weak acid. So this becomes an ice table because we know that 0.1 molar, that's not 100% dissociation. So we can't just simply say, well, 0.1 molar of acetic acid is the same as 0.1 molar of the H plus ion. We know that some fraction of it's going to dissociate based on the Ka. So we need the Ka or the pKa, and then we need to figure out from the ice table to what extent it dissociates. So we'll just write this out generically as HA instead of writing out the full formula for acetic acid. We know that we're starting with an initial condition of 0.1 molar. We don't have any of the acetate ion yet, and we have nominally 0 protons to start with. We know the reaction is going to move from left to right to create some of this stuff, so our change is going to be some minus X, which this 0.100 minus X. This is going to be plus X, and our equilibrium concentrations will be X for each of those. So we can write up Ka is equal to X squared over 0.10 minus X. We can solve this for X via the approximation, and that gives us an X is equal to 0.013, which you should do yourself, convince yourself. Negative log of that, since that is the concentration of protons, gives us our pH, which is 2.87. So that is what we'd expect if we just took the beaker of the original acetic acid sample and dipped our pH meter into it. We'd expect a pH of 2.87 at our starting condition. So instead of plotting this in real time, I'll just keep track of the data. So we now have the data point of 0 milliliters on our x-axis yields a pH of 2.87. We also know that the equivalence is at 40 milliliters, but we have yet to compute its pH. So let's think about the pre-equivalence region. This is why it's nice to figure out what the equivalence volume is to start. We know that that is any volume then less than 40 milliliters, so we can just arbitrarily pick something, and for convenience I'll just pick 20 mils. So let's figure out what the pH of the system is when we've added exactly 20 mils of our titrant. So of course this is a neutralization reaction. We're adding a strong base to a weak acid. We've thought about this in previous videos quite a bit. So that's just going to deprotonate some amount of that HA depending on how much we have. This will go to completion because Kn is very large, in this case the neutralization equilibrium constant. So we can use this to sort of think through what will happen in this system and what we have at the end of this addition of 20 minutes. So you can do this like before when we had the strong acid, strong base example, where you just figure out how many moles of OH are being added to the system, how many moles of HA you have to start with, and then just subtracting the two to find the excess. Or you could write up sort of a pseudo ice table, which I like just to keep track of what's happening in the system as it relates to the neutralization reaction. It's important to know though, when you're using the sort of ice table like this, since you're changing the volume of the system, the ice table looks a little bit differently just because we need to account for that new volume, which we didn't have to do in the past when we were just thinking about an acid or a base dissociating because the volume was constant. So now we just need to make sure we add a little bit of nuance to the ice table to make sure we don't lose track of what is there. So the way that I like to do that is to write up my concentration like I would in any ice table, which was for HA, the initial concentration is 0.1, but I want to know what its concentration is at that moment after I've added stuff. So in order to do that, I would take and multiply by 40, which is milliliters. That would give me the number of moles. And then divide again by what the new volume is, which is 40 plus whatever we've added, which is 20. And so you can work this out dimensionally, convince yourself that this is a valid way to do this, because what that really tells me now is what this concentration is. It's not 0.1, it's slightly more dilute than that because we've added some volume of stuff. So I'm going to use this, this approach just to simplify. We can take a similar approach for the OH because our titrant is also 0.1 molar. We're adding 20 mils of it, but remember the new volume is the same as what it is for HA. This is the same beaker for both of these systems, which is 60 mils. And so the new concentration of OH at the initial condition is going to be 0.1 times 20 over 60. And we are going to make an assumption that there is no A minus, there shouldn't be in the system, and water doesn't matter. Remember, this is the initial condition, so this is like time 0 point, where we had a weak acid in the beaker and we're adding OH. We know these things are going to instantly react with each other, so we're talking about the moment just before they do. So this tells us how much OH there is, this tells us how much HA there is at that. Okay, so what's the change condition? Well, we know already that this is a neutralization reaction, which means it proceeds with very large K, equilibrium constant. So that means all of this OH is going to get used up, and so we can subtract that from this to make it go to 0. And when you use 1 mole of OH, that means you consume 1 equivalent mole of HA, and you make 1 equivalent mole, because these are all 1 to 1. And so if I subtract all of the OH to make it go to 0, then I'm subtracting that same quantity from HA, because I'm destroying it, but I'm adding that same quantity over here, A minus. So now we can sort of tabulate these values and figure out what we have at equilibrium. So just for convenience, I don't normally do this if I'm solving a problem like this, but just so that you can see, I just simplified these numbers so that they're actual values. So instead of 0.1 times 40 over 60, that is actually equal to 0.0667. And so the pink numbers here are the actual values. And so we can see then at equilibrium, our HA concentration is going to be 0.0667 minus 0.033, which gives us the 0.033, so we're exactly half. Subtracting 0.033 from 0.033, I mean, that is 0. That should be intuitive because that is all the OH that runs out because it fully reacts with HA, and that means we have now 0.033 because we converted exactly half of the HA to A minus. So let's think about now what we have in the system, because that's always useful, because our goal then is to figure out what the pH is. And we just tabulated this using the neutralization reaction, but there's no hydronium ion here. And that's because we need to think about what is in the system and how that relates to hydronium ion. And so Now we have a mixture of HA and A minus, and that might give you a clue for what type of system this is. So there's a definition for that type of system when you have a weak acid and its conjugate base. We call that a buffer. And so there's two approaches to solve this problem that we walked through in the buffer section of acids and bases. I could simply write out the dissociation of HA and water and use the Ka in an ice table to then figure out what the equilibrium is and figure out what H plus is. That's sort of the long way. Or I could use the log transform version of that same approach, which is what we call the Henderson-Hasselbalch equation. So I could just now use the Henderson-Hasselbalch equation, plug these numbers in and solve it. And so it's important to know that this region in this type of acid-base titration, you are making a buffer. Hopefully that's clear. You're starting with a weak acid and you're adding strong base, which is actually a way to prepare buffers, right? And so in this region, anytime you're in the pre-equivalence region, you have a buffer system where the pH is then simply just going to be defined by the ratio of those two species, like it has before. You might even see this example right here and say, wow, they're equal parts. And that's a unique type of system for the Henderson-Hasselbalch equation, as we'll see here. So Henderson-Hasselbalch equation is pH equals pKa plus log conjugate base over acid. So I can punch in our values. So the pKa is 4.74, which just came from the negative log of the Ka up here, which we know. And then we have equal parts of these acid and base in the system, which means this goes to 1, log 1 is 0, and so the pH is equal to 4.74, the pKa, and that's always going to be true. Anytime you have a weak acid, strong base system, if you add exactly the right amount to convert half of the conjugate, or half of the weak acid to conjugate base, you have equal parts, this will always look the same. So that's our system. But it's important to note that any volume between 0 and 40, we could have used this Henderson-Hasselbalch equation, and the only thing that changes is the ratio of these two terms. That's all that's happening in that region of the titration, is you're changing the buffer. Okay, so next phase of the titration curve then is the equivalence point, and we've already determined that the volume in equivalence is 40 mils. So that means it takes exactly 40 mils of NaOH at 0.1 molar to completely neutralize all of that acetic acid that's in solution, but no more. So this is the exact stoichiometric equivalence. What we're trying to figure out then is what is the pH of that system. And this is where it gets a little bit trickier, and you need to really think about the question, what do I have in solution after I've added that titrant? So in this case, we have our weak acid plus our strong base, but at the equivalence volume, we're adding equal parts of these two things. So that means all of the HA gets converted, right? So this goes to 0, this goes to 0 because they completely react with each other. And that means whatever our initial HA that we had in the system has all been converted to A minus and H2O. So what is this type of system? Well, hopefully this looks different than the equivalence point at the strong acid, strong base system, because in that case we just had pure water, so we could say, oh yeah, well the pH there is just 7, that's nice. In this case we don't have pure water, we have a weak base in water. And so your intuition would say, well, if it's a weak base, then that means that the pH is going to be greater than 7, which is true. So now we need to think about, well, if it's greater than 7, by how much and how do we know? Well, if you think about this, this is the condition after you've completely neutralized it. And so all you have now is just a weak base in water problem. And so to what extent will this weak base associate with H2O? Well, it's going to be governed by Kb for this weak base. So we just need to write up a new expression for A minus plus water and see how far that goes, and then use that to compute the pH. So that equation just looks something like this, right? We have the weak base, which is really just the acetate ion, plus water. That's what's left over at the moment of equivalence. And we know that the weak base is going to react to some extent with water. It has to. And we need to account for that, because that's going to define how much hydroxide is in solution, which then tells us how much H plus is in solution. And so this reaction abides by the Kb equilibrium constant. We do not have that, but we have Ka, and we know that Ka times Kb is equal to Kw, so we can derive a Kb pretty quickly. which is just 5.6 times 10 to the minus 10. So now we need to think about the ice table so that we can use this Kb. So we need to know what is the initial concentration of A minus here, the acetate ion, after you've completely converted it. Well, remember, you started with 0.1 moles per liter of acetic acid and 40 mils of it, and then you converted every little bit of it into A minus. And so whatever you started with, that's what you have now. But the caveat here always is that in titrations we're changing the volume. So we have the same number of moles of A minus as the original acetic acid because we've literally just converted every mole of HA to A minus, but we've added more volume to the system, so we need to account for that volume in our ice table. So just like we did before, I like this shorthand notation because it makes things nice and clean and easy. So the concentration of A minus is simply what we started with because we converted 100% of the HA, the acetic acid, and the moles of that would be determined by just taking the concentration times the volume, which would be 0.1 times 40, but then we need to divide by the new volume to get the new concentration, and that's simply the volume at equivalence. We added 40 mils of titrant to our original sample of 40, which means that really our concentration has now dropped in half. So just for clarity, I'll write up what the actual value is here, which is just half of what we started with, 0.05. That means we had the same number of moles, but we've just doubled the volume. So the rest of our initial conditions, we don't consider water, we don't have any HA yet because we've converted all of the original HA into A minus, and now it's going to go backwards and make a little bit at equilibrium, and we'll say we have negligible amounts of OH minus. So our change then is going to be some minus X and plus. And at equilibrium then we're just starting with whatever we had left over in the solution, 0.05, and then some amount of it's going to reassociate with water to make some amount of HA XX, so we can write up our equilibrium expression and set that equal to Kb. So that looks like this. Solve for X, that gives us 5.3 times 10 to the minus 6. Remember, X here is not hydronium ion concentration. That's a pitfall. If you take the negative log of this to get pH, you'll get a weird number. So this is hydroxide concentration, so we can go and convert to H plus using Kw. That gives us a concentration of hydrogen ions of 1.897 times 10 to the minus 9. Negative log of that then gives us our pH of 8.72, which, remember, we're talking about the equivalence point. So that was when you added exactly enough acid and base so they completely neutralized each other. And with a strong acid, strong base, the pH of that system is completely neutral, 7. But when we are adding a strong base to a weak acid, because what's left over in that solution under the equivalence point conditions is another weak base, that means our pH is actually greater than 7, and that fits. All right, so the last point here is just that region that's post-equivalence, so we'll just pick 60 milliliters again, but it could be any value greater than 40, which we determined as our equivalence volume. And the same thing is true, so we just set up, well, what's the reaction? Well, we're adding a strong base to weak acid. We use the same approach. Well, what's our initial concentration of HA? It was 0.1. 40 mils of it was our original, and the 100 mils, that's our final volume because it's 60 plus the original. What about OH? Well, it's the same. It's 0.1 because that's what we're starting with, but we're adding 60 of it, so that would give us the moles of OH divided by the new volume is 100. And so in this case, notice that this is the excess. This value is greater than this value. So instead of subtracting OH from HA, we're going to take that from here because we're going to be left with excess hydroxide. So I just wrote that out explicitly. That is written in blue down here, so that's 0.04 and this is 0.06. So when these two things react completely, that's going to deplete all of the HA, and so 0.04 will be subtracted from OH, and we'll add 0.04 over here, but of course that's going to leave some amount of excess hydroxide in this. So what we have at equilibrium is no HA left, plus some OH minus and some A minus. And so really what we have in solution are two bases. We have a weak base and a strong base. And so you could think about this sort of a couple of different ways, and I'm not going to write out all of that because it's going to take me a long time, but you can prove it to yourself that if I were just to take A minus and then say, well, in reality, some amount of A minus is going to react again with water to make hydroxide as a weak base, and that's going to make some contribution to the pH of the solution. That's true, but it turns out that because Kb is so small, it's very, very negligible. And so the dominant contributor to the pH of the system, anytime you're past the equivalence point, is going to be whatever the excess strong base is. So in this case, we can just figure out what the pOH is and then use that to convert to pH, and that would be which in this case is 12.30. So our sort of tabulated data here then is something that looks like this. So if we make a plot of then volume on the x-axis and pH on the y-axis, we'd find it's something like this pink curve, and I've overlaid then the generic sort of form of what the strong acid look like, and it turns out they look very similar. The equivalence volumes are still going to be the same because the stoichiometry is the same, but what you notice is actually more tolerance to pH change in this early pre-equivalence region. And the reason, hopefully, that you understand for this is because we have both a weak acid and its conjugate base in solution at this point. And so we call that the buffer region. And so it's distinctly different from the strong acid and base because you can't make a buffer from a strong acid and base. So this is the buffer region. This is the equivalence region, and this would be our sort of post-buffer region. And this is always going to be true for any weak system that's being titrated with a strong system.